If anyone has taken some basic mathematics, you're probably familiar with Euclidean geometry. Euclidean geometry is just what most people call geometry. It's the study of shapes like triangles and circles in a simple plane. This type of geometry was developed over 2,000 years ago, and it's based on a certain set of axioms. However, later mathematicians challenged one of those axioms, and it completely changed how we thought of geometry. Learn more about non-Euclidean geometry and what it means on this episode of Everything Everywhere Daily. This episode is sponsored by ButcherBox. It's that time of the year when we soon will be settling in to watch college bowl games in the NFL playoffs. When you get your friends together to watch the games, there's no better food to serve than chicken wings. And if you're going to have chicken wings, why bother serving wings from a pizza delivery service or a sports bar when you can serve the best wings around? ButcherBox has free-range organic chicken wings. When I make wings, I just put them in my air fryer for 18 minutes at 400 degrees, and they come out perfect. You can add whatever sauce or seasoning you prefer, but I'm happy with just plain old salt and pepper. Sign up today at butcherbox.com/daily and use code DAILY to get free chicken wings for a year. That's 3 pounds of free-range organic chicken wings, free in every order for a year when you sign up at butcherbox.com/daily and use code DAILY. This episode is sponsored by Factor. I don't know about you, but I have certain things that I look for when I evaluate the quality of something. With my recent order from Factor, I had the opportunity to put their meals to the test. One of my meals was garlic mushroom chicken thighs with garlic green beans. What I look for when I have green beans is how crisp they are. The crisper they are, the more fresh. The green beans in my Factor meal passed the test with flying colors. They were almost like the kind you'd get out of the garden. That's because their meals are fresh and never frozen, shipped directly to your door. With Factor, you can have a high-quality meal in just about 2 minutes. If you want to treat yourself to high-quality, delicious meals over the holidays, head to factormeals.com/EED50 and use code EED50 to get 50% off. Once again, that's code EED50 at factormeals.com/EED50 and get 50% off. Many of you might find the phrase non-Euclidean geometry to be daunting. However, it really isn't. Euclidean geometry is just the geometry that you were taught in school. For example, the fact that all of the angles in a triangle add up to 180 degrees is a part of Euclidean geometry. The word Euclidean comes from the ancient Greek mathematician Euclid and the system that he developed. So before we can get into what non-Euclidean geometry is, we first need to understand exactly what Euclidean geometry is and who this guy Euclid was. Euclid, and that's the only name we know him by, was born about 2,300 years ago. We know almost nothing about his early life, but we do know that he did most of his work in the city of Alexandria in Egypt, which was very much a culturally Greek city at that time. Euclid may have attended the Platonic Academy, which Plato established, and he may have taught at the Museum, which was part of the Library of Alexandria, which I covered in a previous episode. Euclid was a prodigious writer who wrote on many subjects relating to science and mathematics, although many of his works have been lost to history. What Euclid is best known for, however, was his work on geometry. Euclid's book, titled Elements, is his best-known work and is considered the foundational work in the subject of geometry. Elements was so important for the development of geometry that Euclid is known as the father of geometry. And here I should note that mathematics 2,300 years ago was nothing like it is today. There were no equations. There were no pencils or paper. They didn't even have a base 10 numbering system or mathematical symbols like we have today. Mathematics, which was largely geometry back then, was done using two primary tools: a compass, from which you could draw circles and arcs, and a straight edge, with which you could draw straight lines. What Euclid did in the Elements that was so special is that all of the geometric theorems he developed were logically based on just a few simple axioms. An axiom is a simple statement or proposition that is accepted as true without proof. An axiom is usually considered to be self-evident and is the starting point for all the logical conclusions that can be drawn from it, which are called theorems. Euclid laid out 5 axioms, which were the foundation for geometry. Even if you aren't very well versed in mathematics, you'll still find most of these axioms to be extremely easy to comprehend. They are as follows. Axiom 1. A straight line segment can be drawn joining any 2 points. Axiom 2. Any straight line segment can be extended indefinitely in a straight line. Axiom 3. Given any straight line segment, a circle can be drawn having the segment as the radius of the circle and one endpoint as the center. Axiom 4. All right angles are equal to one another. Now, having heard those, your reaction might be, duh, but that is sort of the point of axioms. They're simple, self-evident statements that are the logical foundation of everything else. But before I mentioned that there were 5 axioms, and I only read 4. And that's because the 5th axiom is really what this entire episode is about. And you'll notice immediately that it is different from all the others. Axiom 5. If a line segment intersects 2 straight lines forming 2 interior angles on the same side that are less than 2 right angles, then the 2 lines, if extended indefinitely, meet on that side on which the angles sum to less than 2 right angles. Axiom 5 is known as the parallel postulate, and you'll notice that it's much more complicated than the other 4 axioms and not nearly as self-evident. The thing that bothered many mathematicians about the 5th axiom is that many of them thought that it shouldn't have been an axiom at all. They felt that it was a theorem that could be derived from the previous 4 axioms. For centuries, there were attempts to derive the 5th axiom as a theorem from the first 4 axioms, and for centuries, mathematicians failed. It seemed like old Euclid actually knew what he was doing and had put the 5th axiom in for a good reason. There's one assumption that Euclid never explicitly stated, however, but it's actually really important, and it turns out to have something to do with the 5th axiom. That everything Euclid was talking about was taking place on a flat plane. That assumption was never really challenged, and it's why the term Euclidian geometry didn't even exist for 2,000 years. That's because it was just called geometry. That, however, began to change in the 18th century. A restatement of the 5th axiom was developed by the Scottish mathematician John Playfair. His version, known as Playfair's axiom, says, "In a plane, given a line and a point not on it, at most one line parallel to the given line can be drawn through the point." As mathematicians tried to prove the 5th axiom, they discovered a bunch of axioms that could have been used in place of the 5th axiom that didn't at first seem to have anything to do with parallel lines, but served the same function. For example, one axiom states that the sum of the angles in every triangle is 180 degrees, or the sum of the angles is the same for every triangle. After centuries of trying to prove the 5th axiom, some mathematicians just began to wonder what would happen if the 5th axiom wasn't true. The axioms were the logical basis for geometry. So what would happen if you used the same logical basis in the first 4 axioms, but didn't assume the 5th was true? By not assuming the 5th axiom, it meant that if you had a line and then another point, what if there were either 0 or an infinite number of parallel lines that went through that point? The first person to seem to have taken this step was the man that many people regard as the greatest mathematician in history, Carl Friedrich Gauss. Gauss spent decades pondering this question and, strangely enough, never published any of his conclusions on the subject. All we have are his references to his ideas in letters. However, he was also the person who coined the term non-Euclidean geometry. In the early 19th century, 2 mathematicians independently began working on the problem: the Russian mathematician Nikolai Lobachevsky and the Hungarian mathematician János Bolyai. What they found is that you could create a logically consistent geometry that held to the first 4 Euclidean axioms, but violated the fifth. So it turned out there wasn't simply geometry, as had been thought for 2,000 years. There were actually geometries. The way things are now roughly categorized is that there are two general types of non-Euclidean geometry: elliptic geometry and hyperbolic geometry. Again, these are fancy-sounding words, but not that difficult to understand. Ecliptic geometry is when space has a positive curvature. The easiest example of this to comprehend is spherical geometry, which is the surface of a sphere, or in a more real-world example, the surface of the Earth. In spherical geometry, you can still have the four original axioms, but not the fifth. For example, for any 2 points on a sphere, there is a great circle that will go through the 2 points that would divide the sphere into 2 equal hemispheres. Assume that there is some point that is not on that great circle. Every great circle that can be created through that point will intersect with the first given great circle. In other words, there are no parallel lines. If you make a triangle out of 3 points on a sphere, the angles of the triangle will always be greater than 180 degrees, which sort of shows how the angles of a triangle and the parallel postulate are tied together. Now consider another version of the parallel postulate, but this time instead of there being one parallel line as in Euclidean geometry, or 0 parallel lines as in elliptic geometry, there are actually an infinite number of parallel lines. It turns out that this is a perfectly valid geometry as well, and it's known as hyperbolic geometry. Instead of a sphere that has a positive curvature, in hyperbolic geometry, space has a negative curvature, sort of like being in the middle of a horse saddle. It turns out that if you take a line in hyperbolic space or on a saddle surface and then run another line through a point not on that line, there are no lines that will ever intersect with the original line. In other words, there are an infinite number of lines that meet the definition of a parallel line. Also, in hyperbolic geometry, the angles in a triangle add up to less than 180 degrees. So it turns out that Euclidean geometry is just geometry in a space with 0 curvature, aka a flat plane. If the space curves, you can get totally different geometries that violate the fifth axiom, but still preserve the first 4. Now at this point, you might be thinking that this is all just a bunch of theoretical nonsense. Parallel lines are parallel lines, the angles in a triangle are 180 degrees, and all the rest is just fantasy. However, that is most certainly not true. In the case of spherical geometry, the applications are obvious. When an airplane flies from one place to another, the route it will usually fly is a great circle route across the surface of the sphere. If you've ever been on a long flight, you can usually track the progress of the flight on the flight entertainment system. When doing surveying for projects that span long distances, the curvature of the Earth needs to be taken into consideration. And it turns out there are real-world uses for hyperbolic geometry as well. Perhaps the best-known use of hyperbolic geometry is in the theory of special relativity. According to special relativity, space and time are bound up into something known as spacetime, which can have a curvature. If spacetime has positive curvature, aka elliptic, it's known as a de Sitter space. And if it's negative, aka hyperbolic, then it's known as a Minkowski space. So these non-Euclidean geometries do indeed have very real-world applications. I realize some of the things that I've talked about in this episode may have gone over the heads of some people. However, I assure you that the concepts behind them are actually rather easy to understand. For centuries, mathematicians tried to disprove that Euclid's fifth axiom was in fact an axiom, and they failed miserably. It wasn't until centuries later that mathematicians took a different approach and tried to envision what things might look like if the fifth axiom were false. And it's from that they were able to develop entirely new geometries. It turned out that Euclid's decision to add a fifth axiom was in fact a stroke of genius. A decision taken over 2,000 years ago that has led to new fields of mathematics today. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Peter Bennett and Cameron Kieffer. Today's review comes from listener JSD078-14 over on Apple Podcasts in the United States. They write, "Finally a Completionist Club member. Finally, I slogged down all the episodes. That was an epic ride. I hope Gary has episodes covering the Philippines soon. By the way, where do I get my badge and my fez? Do we all have a secret handshake before each meeting?" Thanks, JST. You can get your membership card at the front desk. The concierge will show you the facilities and all the other secret things you need to know. And yes, I do have some episodes planned about the Philippines. At this point, it's really just a matter of what order I want to do the episodes in. Remember, if you leave a review or send me a boostagram, you too can have it read on the show.